Okay, good morning, everybody. Just sending out a message here to make sure you guys can hear me. Looks good. Okay, I just need one person to say good. Okay. Glad we have a lot of thumbs up. All right, so I guess we're beginning again. It's 10 a.m. roughly. It would be nice if everyone got here maybe a little sooner. Again, I know it's probably your first class of the day, but if I got to get up this early, you guys have to too. So we're going to continue on with the class, starting chapter 1 officially. Again, this is being recorded. Maybe, well, probably near the end of the class, I'll do a little poll to see if everyone's interested in doing the participation marks. So if you guys can hang around, I'll wait till more people enter. Okay, so if there's quickly, if there's any questions, again, you guys just throw them on the chat screen there. I can see them at any time. It's fine. It doesn't have to be related to the content that I'm showing immediately. So I guess I'll begin. So we're going to start with chapter 1 here. Do we have lab today? Oh, I guess I was going to leave that a little later, but we won't be having a lab, but we're going to be having extra lecture time. We haven't really covered anything to be doing a lab on right now, but I can't lose that 3 hours. So I'm basically going to be doing 2 more lectures. I'm sure there's a collective groan going on out there, but believe me, it's a lot easier for you than for me because I'm going to be talking for about 5.5 hours today. So it's just a normal day for me. All right. Okay, so let's start up here. Basically, I did a little short intro the other day. Now we'll actually just start talking about the course in general. Some of these slides are from my DLD1 course, but again, it's just to kind of get us into the mood about the whole course. So I'm sure you guys are well aware of the fact that the digital systems we use today have a prominent role in our everyday lives. We call this time now the digital age. And the technology around us is ubiquitous, and that's basically a term that means we don't even notice it anymore. You are all used to technology to a degree where it's just part of your life and you don't even think about it. I'm sure most of you don't even have, does anyone have a standard alarm clock anymore with the bells on top where you would wind every night? I don't know if you guys have even seen those. You probably just have your cell phones now. A lot of us, you know, I still have a clock on my nightstand. It has a battery backup, but you know, I don't want to say the area where I live is prone to power outages, but there's the occasion where the power goes out, and you know, even sometimes that kicks off. So I think it's rare to hear anyone use the excuse I'm late today because the power went out and my alarm was off. It's just we all use our phones, and traffic lights get us here. Those are all digitally controlled, and our cars are basically completely computer driven. Everything is all electronic, so we're really heavily relying on it. Not to mention, again, all of our communications. We're constantly in communication with everybody. Again, I'm not a big fan of social media in any way. I guess I grew up at a different time where, if you wanted to talk to someone, you either found them or you called them on the phone, and that was about it. So I'm pretty much the same way now. I don't particularly go out there and post things. I just don't see the point to it, but I'm sure you guys do. So in any case, so these digital systems, they're basically used in any point where automation can be achieved. So obviously communication is a huge issue. If you guys ever saw the way telephones started out, they had operators where an actual person who would sit there and patch your calls through to the other people. Those people were eventually phased out, not because of necessarily technology, although it was inevitable, but it was because people were complaining that these people were listening in on their conversations and relaying, secrets to other people. They were kind of being bribed to or paid to. So in any case, clearly it's good that we don't have them anymore, just because the system would be so slow. So we have these automated switches that route our calls or make all of our connections for us. Obviously, it's great. All business transactions, these are all digital. The stock market is totally run by this system now. Traffic control, again, they used to have people sitting out there telling us when to go and stop, right? Spacecraft guidance, it's kind of a big deal there. You don't want to be making mistakes. Medicine has made a humongous advancement in everything, in every aspect, because of digital imagery. Before, doctors would just simply have to guess what was going on. Now we have proof. I mean, X-rays were great and everything, but you couldn't get real-time, views with X-ray, and again, we couldn't expose people to large amounts of radiation all at once. So, those types of situations. Weather monitoring is also a huge thing. We have satellites all over and massive supercomputers trying to figure out what the weather is going to do. I'm sure, as you guys know, any small system can impact a larger system. So it's all well interconnected. Of course, the internet is a very large thing that we're all using, and it's completely driven by electronics. Not to mention all other commercial, industrial, and other scientific enterprises. Again, companies, the most successful ones, are probably using these systems to their benefit. And I do pretty much every day too. I'm constantly using computers to basically aid me in what I do. It's just if I try to do things myself or manually, it would just take too long. It just makes the process so much slower. And again, humans make mistakes, so I use them to kind of try to avoid the situations where I would clearly make a mistake. Okay. So obviously we have digital telephones, digital televisions. You keep hearing this word digital. Digital versatile disk, that's one type of storage. That's what DVD stands for. But of course, same technologies, higher capacities later on. Digital cameras, all of our handheld devices, of course, all that stuff's kind of been integrated into our phones now. And of course, we have our digital computers, which is what our phone is completely based on. It's basically just a portable computer with all these extra facilities. Okay, here we go. All right. So we enjoy music, video downloaded directly to our portable devices, our phones, of course, which have these very high resolution displays and use very complex digital communication networks. So 4G or LTE, and of course, 5G again, which is nothing really any better than 4G. There's just more bands of information. These are just brandings. They're not really necessarily a particular technology. LTE is the proper term. That stands for long-term evolution. It basically means a system that can be built on over time. And again, as we use things, we've kind of come to an understanding that, the interfaces have to be, well, not necessarily easy to use. That's always been my point of view, is that they should be easy to use, but now it's come to the idea where they've gotten extremely eye-friendly, and, we call it eye candy, basically. So they all look nice. But do keep in mind that with all of this stuff, they're actually quite complicated systems. And to make them operate, it requires a precise execution of a sequence of complex internal instructions. So there's a lot of code there to make that system that looks so simple run very well. So it's very easy to say that your phone's operating system is well over 3 gigabytes in size. And that's like compiled code, binaries. That's a lot of code, quite honestly, to kind of be doing all that stuff. Now, again, I'm coming from the perspective when I started doing this stuff where, 64 kilobytes of memory was a lot of memory. So 3 gigabytes is, it's just incredible. Now, again, these are just general purpose digital computers. Now, again, you've probably heard me say this. Again, general purpose computers are basically, they're not really good for one particular thing. They're meant to do as many things as possible. So when it comes down to doing a very specific task, they're just not good at it. So we have to add extra components to do that extra work. So such as a radio. And when I say radio, that means anything that, sends and receives data wirelessly. That's the term, really, not like just FM radio or AM radio or something like that. So all that stuff is done by a secondary circuit. It's simply just told your phone when new information comes in, the core of your phone, and then it handles it accordingly. Also, audio and video decoders and encoders. When you watch video on your phone or you record video, it's not software doing any of the work. It's a piece of hardware. Okay, someone just asked what's the first lab about. Obviously came in a little later. There won't be a first lab. There will just simply be extra lecture time today at 1 o'clock. So again, as I was saying, we have extra circuits that do all that work. If you try to do that work with software, it just can't keep up. We'll have to see about next week's lab. We'll have to see how we're going and how we're progressing to see if we've covered enough material. Okay, as I was mentioning, this stuff, it wouldn't work very well in software, especially 3D games, for example. I'm sure if any gamers in the audience know that if you want to play any of today's games, you can't do it without, you know, some specialized graphics card or high-end graphics card. So these again are dedicated circuits designed specifically to do all this processing. And again, the reason they came out was computers just aren't fast enough. It makes more sense from the perspective of software programming because of the flexibility to do everything in software. It just makes things easier. But when you have to achieve a particular performance specification, you just can't. It doesn't matter how fast software is. It's just the amount of information being manipulated is incredibly large. So for example, if you're watching a full HD video, the image itself has over 2 million pixels. And if we look at, okay, well, what do you need to show those pixels? Well, each color component, which is typically 3 of the image, requires bytes. So you're looking at about 6 megabytes per image. Now, if you take that and multiply that by, let's even say 30 frames per second, okay, you're talking about a massive amount of data, almost 200 megabytes per second to be processed. Now, I know computers are pretty fast, but maybe they can move that much data, but can they process it? Can they do some type of, you know, complex manipulation of the information? And it simply can't. Okay, so we do need these systems that can do that. So again, when you record video or you watch video, there's a circuit doing all that work. Your computer or the computer in your cell phone is basically just telling that particular piece of hardware that does all that work, where do you put the picture on the screen and how big is the picture? That's pretty much all it does. It just kind of offloads the work, and it basically gives it the information. It just says, okay, here's that information. You just do the work. I'll just keep giving it to you as you need it. So it kind of does make a lot of sense that it works that way. So it's just offloading that work to something else. Now, there are, again, some limitations. If you've ever recorded video on your cell phone, you'll notice the files are quite large. But if you watch videos off the internet, you know, some encoded version of a movie, you'll notice the file is quite small. Again, it takes a lot more computational power to reduce that file size to make it smaller. And we just can't really do that in real time. It takes time. So if you ever wanted to encode a movie into a smaller MP4 file, for example, it could take, you know, hours to days, depending on the settings you specify. It's just kind of the way it works. We have to compromise something for something else. If you want a small file size, you have to compromise on time. But we can't do that with real-time video. So the file sizes tend to be quite large. Okay. So what does a digital computer do? Essentially, it just follows a sequence of instructions, which we call a program. So the user can specify and change the program or the data according to the specific needs. Okay, now because this has become, again, the requirement of a general purpose computer allows us to do just a variety of things. They've formulated computers so that they're basically can perform a wide range of applications. So as I mentioned before, the general purpose computer can't do one specific thing very well. So it could take, you know, a number of instructions to do that particular thing, whatever you want it to do. But again, if it's fast enough or it has enough features per se, because again, all digital computers, although they're kind of similar, they're very similar, there's differences between them. For example, you can have an 8-bit computer and a 64-bit computer. There's really not much differences in terms of how they operate, except one just deals with larger data than the other ones. So essentially, these machines, basically, they just manipulate discrete elements of information. Now, again, what those elements of information is, that can just be interpreted depending on what your problem is. So it has to be restricted to some finite number of elements. So again, if it's an 8-bit system as opposed to a 64-bit system, it's just dealing with less amount of information. Doesn't mean it's any worse or better per se. So some information we can have, again, just oversimplifying it, 10 decimal digits is some type of information, or 26 letters of the alphabet, or 52 playing cards, or 64 squares on a chessboard. Again, these are just, again, relatively simple examples, but the pieces of information can be quite large. Again, it all depends on what the system has to do. And the larger the information, it could take more time to process it. So our general purpose digital computer is the best known example of a digital system. Of course, we've seen other digital systems before. And again, I've mentioned a few here already, like video encoders, audio encoders, 3D processing things, devices. These are not necessarily computers. They're highly parallelized devices that do the particular work, but in less time than a computer would. Again, a computer does a series of steps. When we build circuits, we can do things in parallel. We might do 2 things at once or 200 things at once. It kind of all depends how we build it. We have that flexibility. Whereas computers don't necessarily have that. They usually have to do one thing at a time. Okay, so one of the major parts, or the major parts, I should say, of a computer are its memory unit, its central processing unit, and its input-output unit. So basically, computers are usually broken up into these 4 components. And when I say 4, input-output is typically 2. Then how does a computer do a lot of things together? Again, computers are very fast. So even though it's doing one thing at a time, because it's doing it so quickly, it seems like it's doing a lot of things at once. I could make the same claim if you could do 4 billion things a second, you'd be doing a lot of work, or it would appear like you're doing a lot of work. But I think I've asked this question before of you guys. Again, just a way of understanding time. 4 billion seconds is roughly equivalent to about 32 years. Now, it may seem a little odd, but if you do the math, it's quite correct. So 4 billion seconds is a long time for us, right? It's about, if we're lucky, 3 billion seconds is our lifetime, essentially. For a computer, how long is it on for? Right? It's doing a massive amount of work, but again, keep in mind, it doesn't get tired. It doesn't feel any tedium. It just does what it's supposed to do, and that's it. So I can have it sit there and process the same amount of information for literally human years, and it's not going to sit there and say, I don't feel like doing it. I just don't want to do it, or whatever, like things humans do. Is a human okay doing the same work constantly for 32 years? Probably not. It's going to have some psychological effects, right? That's the way humans are, and people know that. If you've ever worked on a line in a manufacturing facility, people don't tend to do the same job over and over again. They want to change things up, and the employer realizes that, so they sometimes often make them do that because they know it's better for them, in the end, so to speak. So yeah, it's just something humans don't want to do. So it looks like they're doing a lot of things, but they're really not. They're just doing, well, I mean, they're doing a lot of things and they're just doing it quickly, is what I'm trying to say. So in any case, okay, so the memory unit, of course, that stores the programs, and it usually is a way of getting to our input and output system and any intermediate data. So memory is like really key to the way these systems work. The central processing unit itself, that just performs any arithmetic, logic, calculations, and data movement. It's just sitting there saying, okay, grab something from memory address 0, do something to it, store it back at memory address, I don't know, 200 or something. That's all it does. Okay, and again, our input and output, that's how we have to get information to our system or out of our system. So again, when you guys use a computer, obviously one of the output devices is a screen, or an input device would be the touch screen, or a mouse, or a network, or whatever. If you remove all those things, it doesn't really do a whole lot of stuff. It can sit there, but there's nothing to really manipulate. Now again, depending on the system we're using, there can be a number of input-output devices. Again, your desktop computer, its major input-output system is, well, you. How do you see what's going on and how do you put information in? Right, so they facilitate that with monitors and mouse and keyboard and whatever else. But servers, they don't have mice and keyboards. They just don't. They're just a box sitting in a room with a whole bunch of other boxes. Their main input-output is a network where people are using things remotely. So they don't even need that stuff. So again, it all depends on what the particular application is. In some systems, like embedded systems, for example, if you have a digital thermostat, what's its input outputs? It's simply what's the current temperature and do I turn on the AC or do I turn on the heat? That's basically its input output. So that system itself doesn't have to be terribly complex, but it certainly is useful, right? We can program it to say, okay, well, change the temperature we're measuring things at to be based on the time of day or the time of week or something like that. So we can make them in effect programmable or adaptable in some way. And it's still a computer. It's just doesn't have to be as complex as maybe the ones we use on a daily basis. Okay, so again, these things are very powerful, or they can be. They don't necessarily have to be. They can perform not only arithmetic computations, but also logical operations. So when I say logical operations, those are basically some type of comparison. So it can be programmed to make decisions based on either internal or external conditions. Okay, and this is quite critical. So they're not just number crunchers. They can kind of take that result and adjust based on it. Now, again, it's not thinking by any means. It would have to be programmed on how to do those types of things. So again, by changing that program, the same hardware can be used for many different applications. What is an arithmetic operation? Basically addition, multiplication, subtraction, division, any type of basic math. Again, when we get into more complex things like derivatives, that's a completely different story. If you guys remember your numerical methods class that talked about doing like higher end operations such as integration, derivatives on sets of data, discrete sets of data using just simpler math, right? So that might be required, but in any case, just simple math. Hopefully that won't affect you here. So again, by changing the program, so by making the systems able to be changed. So instead of not just building a computer that does one piece or one type of work, by making it being able to do more things, we can use these computers in more applications. So with that in mind, by making, again, the processor general purpose or the computer general purpose, it allows more people to buy them or use them for more things, and that reduces the cost of development. I could argue, what are you guys using your laptops for, your desktop computers for? And of course, you're using them right now as a tool in your learning, but what do other people use them for, right? I mean, we don't go to the store and tell our, the salesperson, well, I need it specifically for this. And they'll look at you and say, well, everything in this store can basically do that, right? It's maybe not going to do it super well. It will get done. And what I mean by well is it going to do it with the least amount of power and the lowest amount of cost, or under some particular, restriction like that? Probably not, but it'll get the work done. A good argument, I guess, is, what if you just want to listen to music? Do I need to buy a laptop to listen to music? Well, no, I could buy, do I need to buy a phone? No, you don't. You could go out and find some really, really low cost, MP3 player for maybe a couple dollars that would do that. And it would run on battery, and it would probably have a really good, battery life. It could run on one AA or something. Now, all it does is play MP3s, but it does a very good job of playing MP3s. It can't do anything else. But it's designed specifically for that, right? Whereas, again, general purpose computers, we don't necessarily want to do that because it reduces its usefulness. But again, in particular applications, it might be necessary because then we can reduce the cost. Again, a great example is, the number of microprocessors in your vehicle. There's a lot of them, but they're not very powerful. They do exactly what they need to do, and that's it. And the cost of those individual microprocessors is very low because of it, but it gets the job done. Okay. So, but in the general sense, the advances in our digital integrated circuit technology, this is what we call the process of building them. So you guys have heard the terms like, just recently you probably heard like 10 nanometer, 7 nanometer, those types of terms. That basically implies, well, it used to imply, but it's not entirely true right now. What's the smallest feature size of what they're building? What's the smallest thing that they've been able to build? Now, traditionally, it was the length of a transistor, and I assume you guys have covered MOSFETs, so you do know what the length of a transistor is. But it doesn't necessarily mean that. It's technically, by definition, it's the smallest feature size. It doesn't have to be the length of a transistor. It could be the width of a piece of wiring or something like that. That's why these numbers are quite ambiguous when you hear about them. So you would think 10 nanometers is worse than 7 nanometer, but what is the 10 nanometer measuring as opposed to the 7 nanometer? They could be very well the same thing. The same way they're all built. It's just one is talking about something else, right? 10 nanometer could be the transistor length. The 7 nanometer could be, the wiring width. It all depends. In any cases, they're always trying to make these circuits smaller. So if I can make the circuit overall smaller, it means I can put more things in the same amount of space as I could the last time I built it. So by reducing the number of transistors, we can put more things on a chip in the space we already had before, and the overall cost per unit decreases. And of course, when we go out and buy it, it's cheaper in the end. Even though they can, buy it for less money, and I'm talking about the manufacturers, they can still sell it for less money. So believe me, the stuff you're buying today, you might think is expensive, but overall, it's far, far cheaper than what originally came out. The first IBM PC costs about $5,000 US. Now, if you take inflation into consideration, and again, this was in the early 80s, that would mean these things would cost a whole lot of money. But they don't. They're considerably cheaper than $5,000 or whatever inflation would bring that number to now. And the performance easily is 50,000 times faster than what we had back then. So yeah. Okay. Now, obviously this class is about building microprocessors, but it's kind of difficult to sit back and say, well, how do I build a microprocessor without knowing how to program? So you guys did a little bit of this stuff in computer-aided analysis, learning how to program things. Again, it's very important in my opinion, and it helps us understand how these CPUs work. We have to give them, we did not learn that much. Well, that was not the intent of that course. Sorry to say. Hopefully you got something out of it. We'll hope. So what does it do for us? Well, again, you're trying to build or give the responsibility of doing something to a machine that has no ability to figure that out. Right? So we have to basically be able to break things down into a logical process. Okay. And when you do that, you kind of have to look at, well, what are these steps? Okay, you can't just make assumptions. I could very well easily tell any of you, just walk across the room. How hard is that? Well, think about how long it took for you to learn to walk. It took quite some time. Now it's very easy. You don't even think about how you do it, right? But I'm sure you guys have seen, there's some videos on the internet of, researchers trying to get computers to walk, right? They build these exoskeletons, and there's a company, Boston Dynamics, which is doing some pretty amazing stuff. But believe me, by no means was that an easy thing to do, right? So for humans, certain tasks are quite simple, but do keep in mind we're quite a complicated machine. Whereas, when I'm talking about these logical process, I'm saying, how can you take a problem and reduce it down to simply moving information around and manipulating it and doing basic, decision making. That's what you kind of have to do. So by doing that, you can kind of understand the problems that can come up. So it can improve your diagnostic capabilities when you try to look at something and try to find where the problem is. And it can also improve your communication and visualization skills. If you can reduce something down to its simple steps, then you can explain it better, and you can verbalize it better. I saw a video on the internet of a kid who basically said he wrote the instructions on how to make a peanut butter sandwich, for example. It was some school assignment. And the point was he had to understand that when he wrote the instructions, he had to be clear on them. So his father then followed those instructions to the T. He absolutely destroyed whatever he was doing, right? Because they were just so ambiguous, these instructions. So the same thing can be said in this case. So if we're too ambiguous, we can't expect the end result to be good. So at some point in your career, you will likely need to program something. Now, I do need to stress here that going into the engineering field means that inevitably someone is going to pay you to do some type of analysis into something. Now, computers are wonderful tools for doing analysis, but why would someone pay you to do a work that a computer can do? It doesn't make much sense, right? So there must be some limitation on what the computer can do, and it needs some type of manipulation from some external thing, being you as a human. So a lot of these engineering tools that you do use or will use, they will perform some specific computation or some calculation, but they have to be guided on where to go next or on some type of special consideration. And this is all usually facilitated by some programming mechanism. So a lot of these tools have ways of you kind of interacting with them or creating automation to make them do better work. So it's not unusual to see that in today's tools. And that's what makes them valuable, especially with a human. If a human knows how to use that tool specifically, and then they can automate those procedures, it makes the overall system worth using. So someone asks, what's the best programming languages to learn for the industry nowadays? Well, it all depends on what your problem is. And this is one of the issues I have with the science of programming or computer science, is that whenever a particular problem got difficult to program, rather than someone programming that problem, they came up with another language to do it easier. And that seems to keep happening over and over again. So that's why we see so many programming languages out there. You guys obviously heard of Perl or PHP or Python, or there's just so many. Rust, Julia, I don't know. There's so many out there. As far as what I can say, again, I'm a circuit designer, so I'm always looking for performance. And when I use computers, generally to do some type of calculation, I'm also looking for performance because the computations I'm asking are quite large. So I always program in C because that guarantees me the better performance. Now, that being said, it's a lot harder to do. There's other languages out there where, yeah, you can program something quite easily. A couple of years ago, I was doing some kind of just early analysis into a problem, and I was using was it Python to do this calculation, because someone kind of made a tool that worked with Python to do it. So I was running this calculation. It was just taking forever. It would take so long. And at some point, because I had to run many scenarios of it, I just said, okay, I'm just going to rewrite this in C. And I did it, and it just ran so much faster. I don't mean like 2 or 3 times faster. I'm talking thousands of times faster. Okay. So again, it all depends on what the situation. Because of its efficiency. But again, will you guys need that? Probably not. But if you kind of understand the basics of C or basic structured programming, you can really learn anything from there. It's nothing stopping you from that, right? So, but if we start with very high level languages, you might have some difficulty understanding, the limitations of moving to a language that's lower level. So C is intended to be low level because of performance. It was really, when it came out, it was intended to be just one step above the native processor's language, which is what we call assembly language. And every CPU has a different assembly language. So that's what's nice about C, is whatever you write in it can usually be turned into, that native language with very little overhead, typically. Okay, so again, I want to stress that learning the program will definitely benefit you. So again, what language is best? It all depends what industry you go into, what very specific area it is, because again, they have very different requirements. If you're into web development, of course you're going to use a completely different language there. And again, those languages are intended for faster development, not necessarily high performance. What if you go to a website and the website is slow? You're going to call up the company and tell them, oh, your website is really slow. They'll just kind of laugh at you and say, get a better computer. And that's usually the intent of most companies. They don't care about performance because it's not their concern. If you want something to run faster, just they put the onus on you to get it to do that way. But if you're if I'm a game developer and I'm making games for example, an Xbox, and the game is slow, what's going to happen? Well, you can't go out and get a faster Xbox necessarily. They're all the same. So now the onus is on me to make sure it performs better. So, and if I don't, my game's not going to sell well. It's going to get bad reviews. No one's going to want it, right? So I have to go out of my way to kind of improve the performance. So depending on, the industry, it kind of all depends, right? I can give you a great example of a student. Again, this was a number of years ago. And I remember the student sitting in the front of the class, and I remember them asking the question, I'm in, I forget what discipline they were, environmental engineering or something. This is when we had to teach computer-aided analysis to everybody. And they said, when will I ever learn this? When will I ever need this programming thing? And it turns out when they went on their co-ops for engineering, guess what they were doing? They were programming stuff. Then they did some master's work. They came back for a master's. They were doing programming. And then guess what they're doing now? They're working for actually one of our profs still, and that's all they do is programming. So for someone who had no desire to do it, it just turned out that their road in life kind of went that way. It's not necessarily that that's what they're doing is strictly programming. They're doing some type of engineering, but it requires them to be programming. That's what it is. Again, computers are a tool, and we use them to get work done. And that's what this person is doing. Okay. All right. So, programming computers. Well, it's very important to understand that computers follow the instructions they are given without fail, including the ones that will cause faults, because they simply don't know any better. Now, this is kind of important because if we were to put in that type of mechanism, systems that can detect faults before they happen, it makes the computer slower and potentially makes it more expensive because it requires more circuitry to make those types of decisions. So it's one reason we just don't do that. So you just look at them as simple machines with amazing math and memory skills. Okay, so we can ask it to do any type of math work and it will be correct. And we can have it store and retrieve information and it won't forget anything. Okay, that alone is pretty impressive. Again, most humans can't do that type of stuff. There's probably some humans out there that can, they're very good at math. They're doing mathematical computations. But we still have the problem of, okay, well, how do I feed that information into that human? How do we get that information? That's where your memory skills come from. So again, humans only have a limited amount of capacity for processing. Again, if I go back and say, what is the origin of the word calculator and computer? Calculator was a job. It was a job for someone who would sit down and do math. They were just adding numbers up or doing some type of mathematical calculation. And a computer was another job. It was someone who oversaw calculators or all these people and took their results and kind of, summarized it in some way, right? They were kind of like the overseer. And if you can imagine, like in the 1950s, for example, before computers were mainstream at all, if calculations were being made, it was just a room of people just doing math all day. And, someone just kind of taking those results and putting it together. That's all it ever was. So obviously that's all been replaced. Those people have all been replaced with computers, but do keep in mind that, it's not like they're unemployed or anything like that. They moved on to being the people who program computers, for example, right? Or other tasks. So we have to take whatever process we're given, the problem, and we have to reduce that into the language the computer can understand. Now, again, given that there's so many different computers out there, this creates a little bit of a problem. Everyone, or every computer manufacturer, I should say, CPU manufacturer, has a different interpretation of what is optimal or good design. So we have literally tens of thousands of CPUs out there that all have different languages, and some are long gone, they just never went anywhere, and some are obviously mainstream. So it kind of makes it difficult to how do I take a piece of software and make it run on different computers, regardless of their language. So we have software tools known as compilers that translate these higher level languages like C or Python or whatever into that native computer code. Okay, so but do keep in mind, whenever we use a higher level language, we're compromising on something. All softwares work on all computers I know. That's what someone says. Well, not really. You can't get every program to work on every computer. Again, does everything work on your cell phone? Not really. MATLAB, for example, there's no build for your cell phone. They don't make it for your cell phone. They make it so you can use your cell phone to run MATLAB programs, but it's not actually running on your phone. They run it on a separate computer and then they send the results to your phone. So there's limitations to what different computers can do. So for example, your phone does have a computer in it. It can do work, but it has this terrible limitation that what happens if it gets too hot? What does your phone do when it gets too hot? Okay, so he's saying on Dell and Lenovo computers. Well, Dell and Lenovo computers, those are just IBM PCs or x86 computers as we call them. So they're effectively all the same. Again, just to let you guys know, there's very few companies in the world that actually make laptops. So Dell, Lenovo basically contract the same companies that actually build their computers. They're just branded as Dell or Lenovo, basically. So they're just get a couple people that say, oh, I'm going to start up a company that makes computers. It just doesn't work that way. Again, based on what we require today, what we expect today. Now, you guys may have heard the story that Apple started out of, whatever, Steve Wozniak's garage or something like that. Well, the computer back then was much different. They were very slow. They weren't terribly functional. And yeah, I mean, you could put them together like that because this was before we were even building, again, production level computers. They were very rare. And again, we didn't expect much from them. Now, I don't think any of you would, if you used one of those original Apple computers, you would just sit there and say that's all it does. And again, that's it. Okay. Could Elon Musk put together a computer? Probably not. Amazingly enough, Elon Musk is, he's a smart guy for some things, but and maybe he can convince people to invest in something, but to build a computer, that's way outside of his skill sets. Just saying, again, it's there's not one person in the world today who knows how your standard Intel processor works. Now, as silly as that sounds, then how does Intel build them? They have teams of thousands of people that put these things together. So you could say there's someone there who kind of knows the overall idea. It's just like saying, do you know how a car works? Well, yeah, you put it in gear, you press the gas, it goes forward, or you flip the gear, you put it in reverse, and it goes backwards. It's functional operation, but can you sit there and say, what every part does in the vehicle, and you can be knowledgeable on all those parts? No, you're going to have someone else who knows everything about this part and someone else who knows everything about that part, and that person doesn't even know, so he's got a team of people. So just the way things are built today from the perspective of performance and not necessarily functionality, it makes it harder to make something better. Again, today's cars, they're not the way they originally were, where you just had an engine and that was it. Now they're a complicated system where the engine has different parameters which make it operate in different modes for fuel efficiency or for whatever. And that's never what it was when it started, right? It was just, can I get this engine to run so I can move this car? That was the intent. So things have certainly changed. Anyway, getting back to the slide here. So higher level languages will always require more resources from the system for it to run correctly. So as we move up on the scale of higher level languages, for example, C will create potentially a lot of instructions for the computer, but maybe not that many in regards to how many lines of C code there are. But if you start getting into Python or these higher level languages, it creates far more code, uses far more memory. And if you're fine with that, that's okay. But again, from our perspective, and I just want to get back to that analogy with your phone. Can your phone run every program? No. And I think I've asked other students this. What happens when your phone gets too hot? It will tell you, I need to cool down, or maybe I have to turn off, or it's going to throttle back its processing speed, right? Or the battery is just not going to be operating as well as it should. Batteries are very particular things. You have to, be pulling so much current out of them at a particular time or so much voltage it has to be operating at, and for them to work correctly. And if you run them out of spec, they just don't work that well. So there's limitations when we're under constraints, and that's something to kind of understand about electrical engineering. There's always a constraint. We just don't have the unlimited computer power that we can just get everything from. That's kind of where computer science and electrical engineering differ, because computer scientists always assume, generally speaking, that they have access to unlimited computational power. And that's not necessarily a bad thing. That leads them to being able to solve bigger problems. But for us, my problem is, okay, can I get it to run fast enough under this consideration, or can I get it to run long enough with this amount of battery power, right? It's a completely different constraint. So again, that kind of changes things. So in any case, when we're programming, we always have to make the assumption that the computer knows nothing, and it does. It knows absolutely nothing. So we have to kind of facilitate that in some way. Okay, so we have to be aware of the limitations of what we're doing. Okay, so computers need to be constrained when performing calculations. This is something we definitely need to be aware of. So here's just a great example. When do you stop calculating 2 over 3? So you guys know, okay, well, what's 2 over 3? Well, it's 0.66. Is that correct? Well, no, it's 0.6666666666666, and I can keep going forever, right? Because it never stops. Now, eventually I could put a 7 there, but, well, if I put that 7 there, what is that? What have I done? I've changed the answer. It's not correct anymore, is it? That's not really the right answer when I put that 7 there. I'm rounding up. And when we round up, we have to understand it sounds right, but what on the amount of time it takes me to do this calculation. But other ones, we have limitations. So it may not be possible to represent that whole number. So we have to have a certain amount of space or bits reserved to store certain types of data or information. So we limit the bits to limit the time for computation. So if I limit the number of digits I use for my calculation, let's say I only make it 4 digits, a fractional or fractional 4 digits. When I do 2 divided by 3, it's going to be 0.6667, and that's it, I stop. And you can see I quickly finished, and I move on to the next operation. But knowing that, that limitation is going to perhaps cause some error in my calculation in the end. Okay, we always have to kind of be aware of that. So again, limiting the bits results in limited resolution for whatever information we're using. So again, not all computers are created equal. They have their specific limitations, and some are better suited for certain problems than others, but certainly at a cost. So an 8-bit computer, how is that any better or worse than a 60 or a 64-bit computer? Well, an 8-bit computer is certainly going to be cheaper because it's smaller. I can put more of them in the same amount of space I could put than a 64-bit computer, but I'm going to be limited on the information that I can manipulate. But I've accepted that you know, that limitation, right, or that compromise. Okay, so if I do need a lot of shall we say bits for computation, then I should look at maybe larger computers, right? Okay, so you guys may remember this slide from, well, last year. It's basically talks about how we put numbers together. So when we look at numbers in general, and when I say numbers, I mean a series of digits. It is just a series of digits placed together. But when we do write numbers down, we do realize that where the digits are placed indicates its magnitude or significance. So anytime I write out a number, it's all relative to the numbers beside it, right? So if I write out 10, it's telling me that 1 is more important than the 0. Or if I write out 235, which digit is more important? Well, I know the 2 is more important based on its placement, right? So the digit itself is a actual single glyph, I guess I would say, where it's 0 between 9. That's a digit. A number is a collection of digits. Okay. Now, R is usually our base. Now, of course, because we're human, we usually kind of agree that the base is usually always 10 when we're writing out numbers. Well, that's what it is in most cases, but when we get into circuit design, we sometimes like to change R. Especially we make it 2 for binary, but we'll get there soon. Okay, so if we kind of put this all together, I can say any number is represented by a series of digits where X is that digit, Xi is that digit, and R is the base, and I is the placement of that digit. So where is the position of that digit when I write out the number? And when I is smaller, it's the least significant, right? So when I is 0, my significance of the number or the digit is just its actual face value. So 235, that 5 is in position of 0. The 3 is in position 1, and the 2 is in position 2. So the 3 gets multiplied by 10, whereas the 2 gets multiplied by 100. This is just an equation to kind of visualize the idea that values or numbers that we see are just a collection of digits. It just makes it easier for us to understand binary numbers. Okay, so it's just a collection of digits. Now, for example, Roman numerals, I think you guys have seen Roman numerals. They're not, their actual value of their digit isn't based on its position, so to speak, its overall position. It's based on relative positioning. So for example, if I want to write the letter 3 in Roman numerals, I write 3 I's. But if I want to write a 4, I write IV, which means 5 minus 1. So the position of the I with respect to the V kind of indicates something, right? So that all kind of falls apart here. So we don't use that here. Here we're saying specifically its position, its absolute position indicates its significance. So the higher the position, the more important the digit is. Okay, so again, here's an example. If I have my base is 10, again, just because we're human, and this is the number I want to represent, right? It's a number, but we can look at it as a series of digits where its position is very important. So the digit 4 is in position 0. The digit 3 is in position 1. the digit 2 is in position 2, and the digit 1 is in position 3. Again, 0, 1, 2, 3. Now the 5, because we're after the decimal place or the radix point, this is in position -1, the 6 is in position -2, the 7 is in position -3. So we take the digit and multiply it by 10 to the power of its position. So this number can be easily rewritten as its digit multiplied by r to its power of its position. So I can see there's the 1 times 2 of 10 downstairs. So I don't understand quite what that means, unless that's a spelling error. So we've basically broken up that number into its series of individual digits. Oh, 10 downstairs, you mean this? The subscript of 10. That's just indicating the base. Now, again, generally whenever we write every number, we assume it's base 10. That's just a human thing to do. Okay. However, in our particular work here, when we're dealing with binary systems, we use a variety of bases. Generally base 2, base 8, or base 16. So we have to be clear on what the base is because it changes the interpretation of the number. Okay, so when I write this out, it means this number is in base 10. So its actual value would be calculated this way. Now, of course, I can say this number here is just equal to 1,234.567 without a base, that I know. But if this was an 8 all of a sudden and not a 10, then I would replace all these 10s with 8s. And this would be a very different number, right? It's still a number, it's still a valid number, it's just in base 8 instead of base 10. And if I convert it to base 10, it wouldn't be, 1,234.567. It'd be something completely different, right? So it's just a different way of, again, looking at numbers. All right, now when it comes to computers, and again, the computers we see today, I should say. Well, I'm getting to that right now. Why do we use 2 for? So again, you guys, I'm assuming you studied MOSFETs to some degree. When we operate MOSFETs in their digital mode, they only have 2 modes of operation, on and off. So we're going to use that to our advantage. Now, it's possible at some point in the future that we might have circuits that have more than 2 modes, right? This whole quantum computing thing, for example, could lead us to something different. But for the most part, the way we build circuits today, it all revolves around just on and off, or these 2 modes. Okay, so when we operate these transistors, they only have these 2 modes on and off. So it makes sense for us to use a base where there's only 2 states, or base 2. Okay, so why do we use them in these 2 modes? Well, again, unfortunately, most of your time here spent in engineering will be discussing ideal situations. And this is just the way we learn. We have to kind of understand how things work, and then we'll apply noise and all those particular things to see issues that can come up. In terms of electronics, noise is something that is still something we have to be quite aware of. So also the idea of using 1s and 0s kind of works to minimize noise. So let's just say, for example, I interpret a 0 as being a value from 0 to 2 volts, where I interpret a 1 as being from 3 volts to 5 volts. So now let's say my noise on my circuit is an additional 1 volt. Well, if I have a 0, which is between 0 and 2 volts, and I add 1 volt to it roughly, it's still going to be considered to be a 0. Whereas if I have a signal that's 3 to 5 volts, and I add 1 volt to it, it's still going to be a 1. So digital systems are kind of tolerant to noise. Whereas analog systems, and I'm sure you guys did some work with some analog systems, just a little bit of noise can throw the system completely off. So it's one reason we kind of like digital systems, because it's tolerant to noise. It can handle a certain amount of noise before the system fails, where analog systems, they can't. So it's far easier to build a digital system than an analog system. If by some means, what do you mean by adding 1 volt? Let's just say there's some type of noise on the system and 1 volt gets added to your signal. That's what noise is. It's kind of the addition of extra something to your signal. It could be an extra current. It could be an extra voltage. I might even remove a volt. Then what happens, right? I mean, I don't know if you guys have seen this operating in practice because you're so used to these circuits operating so well. This is one of the problems with digital systems, is that we don't see the end result of noise. So again, if I have a signal that's between 0 and 2 volts, let's just say it's 1 volt, and add 1 volt to it, it's going to be 2 volts, but a 0 is still considered to be between 0 and 2 volts. Even though I added 1 volt to that 1 volt, it's still considered as binary 0. So even though I added noise, the value of the signal did not change. Okay, I don't know if you've ever seen, just some TV show or some TV movie where they're trying to communicate with someone, and they, you kind of hear static, or they can't hear the guy on the other end of the line or something, or they show a picture on the screen and it's all kind of fuzzy. Again, these are rare things to see today. When I grew up with old-fashioned TV, over-the-air TV, you had to sit there and move the antenna around to get the best picture. Now with digital transmission, you'll never see a fuzzy picture or a picture with static. But I can tell you, when we had that type of TV, and again, this was maybe 15 years, the picture and things, and you're tuning in the radio station, you hear static. That's the interpretation of noise as a signal. So again, with all these digital systems, we've gone out of our way to kind of eliminate noise, but you have to be aware that it's there and it has to be dealt with. Now, if you've ever tried to watch digital TV, let's say you have a satellite and there's a storm outside, what happens? You're going to see a picture on the screen freeze or something. It's not going to move, or it's going to move really slowly, or it's going to get blocky or distorted in some digital way, but it's not going to look like static. It's because the receiver isn't, it knows the information it's getting is wrong, so it kind of ignores it, but it's waiting for good information, and it can't update the picture correctly. That's, I guess, the best analogy we have for noise today with digital systems. It just kind of just cuts out, but you don't actually hear any static per se. Okay, so with this idea of one wire having a state of either on or off, no matter how it's, whether or not it's voltages or currents, it's still an on or off signal. Okay, so someone has a question. So if your digital system is at 1.5 volts and it can be interpreted, oh, hold on a second, at 1, then 1 volts get added, now it's above 2 volts, but under 3. Okay, so there's that place between 2 and 3 volts is considered a transitional range, so it doesn't know. But if I add too much noise, then the system is obviously vulnerable, right? And this is a problem. You can't have too much noise to the system. If you do, then it's not going to work. There's nothing you can do. If I'm talking to you in a room and we're talking and everything is fine, and then all of a sudden we hear some really loud noise, someone turns on some really loud music, and I'm talking to you and you can't hear me, there's nothing we can do to stop that from happening. Like, the medium has been manipulated, right? Someone has come in and added more information, and so much so that it's distorted our communication, right? The only thing I can do is switch mediums, right? Use a different wire, or I write things down on paper and you read it, right? A different way of communicating, right? But that particular communication method that we were using, which is just using, sound, it's been tainted. Okay, we can't do anything about it. So then we have to put in maybe some type of noise protection. But again, we can do this, but it comes at a cost. So if I add 4 volts to the 0 volts, if I add 4 volts to the 0 volts, it will make it go from a 0 to 1, yes, and then the system will be confused, right? Now, the important thing about digital computers is because they're always processing information. If one of these bits should happen to switch from a 0 to a 1 or a 1 to a 0 during processing, the system is completely tainted. Everything that it's going to do after that point is potentially um, like just damaged, right? Its next steps can be altered, right? Again, if I'm talking to you over the phone and I'm giving you directions to go pick something up, and you interpret me saying left as right, what's going to happen? And I'm not telling you street names or anything like that. I'm just saying, okay, go 1 block, turn right. Now go 2 blocks, turn left. Now, if one of those instructions gets screwed up, or the distance I said, if you interpret me saying 1 instead of 2, you're not going to end up at the right point. Okay. Now, I should have to say it's very rare to have that amount of noise where we can lift a signal up 4 volts. It's certainly possible, but it's rare in just normal human life. If you're in a very large industrial plant beside a very large machine or generator, it's very well likely it can happen. So in those particular cases, we need to have better protection mechanisms. So you may have heard of the term industrial computers and things like that. And these will be computers where, they're shielded to prevent that type of situation. Any computer sent in space, I don't know if you guys ever seen videos of this where these guys are putting these things together. Everything's wrapped in foil. Um, all this kind of stuff is happening. Again, they have to watch out for all this different type of radiation, noise from other sources. It has to be done. So the same thing can be done here. And you might have seen, if you ever open up an electronic and you see a metal cage around it, that's there to prevent some type of noise. Okay. So it is possible this can happen, but for the most part, it doesn't happen often, but you do have to design around it. And the computers you guys use today, of course, they've considered that, but they also know that there's no guarantee in what you use. Again, when you buy your phone, and if anyone has ever read the end user license agreement, which I'm sure they haven't because it's usually like 80 pages, it basically says in there that, if anything goes wrong with this thing, too bad. It's not our problem, right? Because it's a consumer device, it's considered an entertainment device. It has no, if something goes wrong, oh, well, too bad. That's just the way it is. Whereas other devices, for example, if you have a ventilator and you're connected to it and you're kind of depending on it to breathe, they're going to be a little more concerned on its reliability, and they're going to have better circuitry and their noise prevention, a whole number of things to prevent that from happening, right? Where the system's going to fail. Okay, I'd like to move on from this slide. So again, this is the whole reason we use ones and zeros, is to kind of minimize noise. So now if just for example, let's say I had a system that used 3 states. So there were 0, 1s, and 2s, for example. And I changed the voltage range. So, 0 was between, I don't know, let's say 0 and 1 volt, and a 1 was between 1 and 2 volts, and a 2 was between 3 and 4 volts or something like that. You can see my noise margins, the amount of noise I can add or that I can tolerate, I should say, gets lower and lower and lower. So again, this is kind of why we stick to 0s and 1s. Mostly, again, just because the transistors operate in this on and off mode. That's why we do it. So our whole method for building digital computers has kind of all relied on the devices we use. And transistors, again, are devices we can build, but we can't just sit there and say, okay, let's make them have 3 modes of operations or 4 modes of operations. It just doesn't kind of work that way. We can build them, but we still have to operate under the rules in which they operate. We can't just build them and make them work the way we want. That's not what's happening. So every time we make them smaller, I mean, that's good that we've made them smaller, but the rules in which they work sometimes change a little. So we still have to kind of deal with that. So maybe if we add a little bit of this material or that material, we can kind of make it get back in a spec. But essentially, that's what's happening. That's why it's so difficult to make these circuits smaller, is because we have to still make them work under these rules. And that doesn't necessarily happen so easily. Okay, so again, taking on this idea, well, there's different types of transistors. Someone asks how many kinds of transistors there are, but for digital systems, we usually just stick with MOSFETs, primarily because they're the cheapest to make. It's amazing how cost basically determines everything. There's other transistors that are far faster in terms of switching. Bipolar, for example, can switch at extremely high frequencies. but they cost more money to build. And could we build faster computers? Yes, but we can't cool them, which is a particular problem. So I can make a computer that runs in 100 gigahertz speed if I want, but I can't cool it. And it would cost a whole lot of money to build, like a lot of money. And is it really worth it? And that's the situation. So yes, there are different types of transistors out there, but we only usually use the ones that are more commercially viable, I should say. Yes, well, overclocking can cause noise issues depending on how the circuit is built. Again, do keep in mind when we're talking about overclocking, you're saying, you know, this clock is running in the gigahertz of speed. There could be some stability issues there. Okay, but again, that really overclocking, it's not so much the noise issue is that the circuit can't perform the operation quick enough before it needs the results. So that's usually where the failures happen. Okay, so here's an example. Again, using the same premise, here's the number I've given you. Now, it certainly looks like a larger number, but do keep in mind when we use smaller bases, the number of digits is going to increase. It just kind of has to. So I have 11 integer digits. When I say integer digits, it's the ones before the decimal point, and fractional digits are after the decimal point. Now, clearly, if this number was base 10, you'd say, oh, that's a really big number, but this number is only base 2. So now if I take its position, each digit position, and I multiply it by 2 to the power its position. So again, starting here, this is position 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is position 10. So we start there. 1 times 2 to the 10 plus 0 times 2 to the 9 plus 0 times 2 to the 8. Now again, we can just drop the 0 entries if we write it out like this, 1 times 2 to the 7, and so on and so on. So when we get past the decimal point, this again is position -1, position -2, position -3. So you can see position -1, position -2, position -3. And if I work this out and do the calculation on my base 10 calculator, we will see that this is the end result. Now, you'll notice that this is very close to what I did before, the number I showed before, 1,234.567. Why couldn't I get the 567? Why do I got this 625? Any thoughts there? Give you guys a second to answer that one. Anybody? Anybody? Well, we simply just didn't leave enough room. That's really the situation. 3 binary bits is not enough space to represent 567 or 0.567. It just doesn't work. If I use 1 binary bit, I can either represent 0.0 or 0.5. If I use 2 binary bits, I can represent 0.0, 0.25, 0.5, 0.75. If I use 3 binary bits, you can see where I'm going with this. So I need far more binary bits to represent that. Mice. 0.567. Just can't with 3 bits. It's too bad. Okay. So let me just see if I can, just give me a moment here. I just want to pull up a quick example. Here we go. I'm sure you guys can see this okay. So this is a tool where we can see the output of some numbers here. So I'm going to take 1, 2, 3, 4, 5, 0.567. And I'm going to give it to me in binary output. So again, those are the digits we saw earlier, but here's the fractional digits. So for me to get 0.567, you can see I need a certain number of digits. In fact, I'm not even sure how many I need. Let me just do this again. 567. Oh, that's how many I need. There's not more than that. So if I put these together, I should get 0.567, I think. I'm assuming this tool is operating correctly. Yes. So I certainly need far more decimal digits to represent this number, or binary digits. Now, typically, every decimal digit requires about 3 binary digits. So just again, when I said the 1,234, I can see 4 decimal digits there. How many decimal digits did I need here? About 11. Okay, so if I take the 4 multiplied by 3, of course, that's about 12. So that's about on par. It's not really exactly 3. It's more like 2 point something, but it's roughly it. How come we only need 3 to represent 6 point? Okay, well, what is 0.625? 0.625 is it's kind of a multiple of 8. Let me just pull up a calculator here. Just bring it over here. So again, if I take, what is 0.65? I think that's 5 divided by 8. Yeah. So 5 divided by 8 is 6.25. Sorry, 0.625. That's why that works out quite well. Now, again, if it was 0.626, well, that's a different story. I'm going to need more digits that way. So again, it all kind of just depends on the numbers we use. So one might say, for my particular problem, it's in my favor, and this is something we actually do when we build these systems, to kind of pick numbers that that end up with these nice decimal places. So if I come up with numbers, for example, that I want to use in my digital system, I want to pick numbers that have very small fractional bits, if any. So we try to build it so that when we multiply by numbers, we only pick these particular numbers. Now, this isn't something you guys are really going to explore until maybe in your 4th year. There's a class called digital signal processing where they might touch on that, where picking numbers that have fewer binary bits are, can result in faster operation because we don't need to multiply all those bits together. Again, the 0.625 is just because we only need 3 bits to represent it. I only need 3 digits to represent 0.625, where the 0.567 I used in the earlier example, I needed at least probably look like 8 or something like that. Again, if you want accuracy, it comes at a cost of bits. We need more and more bits to represent them. Okay, but just some numbers don't necessarily work that way. Okay, it's coming up on the end of the lecture. I just want to get through this one slide here. So if we just look at if all the integer bits were ones in this particular case, and I have 11 integer bits. So if I sit there and actually calculate, well, what is the number if I make all those bits one? And if I kind of go through, I come up with a number 2047. Now, it may not seem like a particularly interesting number, but I know something about 2047. Well, I know that 2048 is 2 to the n. So 2047 must therefore be 2 to the n minus 1, where n is 11. So I can sit here and say, if you give me n bits, I can represent any number between 0 to 2 to the n minus 1 as an unsigned integer. So therefore, I can't have a sign. It's got to be positive. Okay. Now, why is it 2 to the n minus 1? Because we need to leave room for 0, because 0 is part of our representation. If I was going from 1, starting at 1, then I would go from 1 to 2 to the n. So I only have that many numbers that I can store this way, unique numbers. So if n is 8, for example, 2 to the 8 is 256. So I can only represent numbers between 0 and 255. If you have more numbers to represent, it's just not possible to fit it in 8 bits. I need to add more bits. Now, that's not necessarily a problem, but it just means I need more storage. I need to have more places to store those bits, or I need my system to be able to accommodate those bits in some way. It's just saying that there's a limitation. So we can't have numbers larger than that. Even your computer has an inherent limitation on the number of digits it can represent in a number before it has to do some kind of trickery to kind of add more numbers to it. When I say trickery, it's like combining multiple bit numbers together to build larger numbers. It's not really tricks, it's just, it's going to come at a cost, more computational time to handle it than it would have in general. Okay. interested in using clickers as a participation marks. Hold on, I gotta press start. Here we go. So, are you interested in using the clickers to add participation marks? So therefore the projects will not be 100%. Okay, so everyone's asking me what are the alternatives? Well, again, Kahoot and all these kinds of things, I tried using Kahoot, I don't really quite understand it. In terms of how I can use it in this scenario, and then there's situations on how do I get the information out of it, get it back into my system when I'm marking, and there's a cost to using those types of systems. Depending on the number of people involved in the class, they can charge for it. And I'm pretty sure no one here wants to spend more money on this class than they absolutely have to. So the one solution we have, the university is piloting a new system called iClicker, and I'll post something on the announcement so you guys can create an account. It doesn't cost you anything. They're paying for it, right? Which means you've already paid for it. And what it basically is you download an app on your phone, and when I put a slide up on the screen and when there's a question, the picture you see on the screen, like the slide you see here, will appear on your phone, and you pick an option between A and E. So there are at most five possible options. And based on that, you get credit for if you get the correct answer. Now, it's one way of getting participation marks. It's nice to see that 44 people haven't answered, which means 44 people may not actually be listening at the moment. It's kind of a method for me to understand whether or not you guys understand the topics. So I can go back and kind of review things, because again, sometimes people don't raise their hand when they don't understand things. They don't want people to know or something. It's just a method, and it's also helping you to see, do I really understand this topic? Or, oh, why didn't I get that right? Or, oh, maybe I didn't understand this very well. So it's just basically a feedback system, and it's really nice now because I can't look at your faces. Normally in class, I could kind of look around the room, and if I see like an odd look on someone's face, I can sit there and I can easily determine that person doesn't understand the topic. I have no way of doing that right now. I have no feedback system other than what you guys are telling me in the chat. Someone asked, is there an alternative to participation marks? Well, again, with the course content the way it is, I can't really offer you guys any tests because people will cheat, or they'll use whatever source they can. In fact, in some cases, when I ran that I'll just kind of do based on the number of answers I get. It'll tell me how many people have responded. So, obviously I want it to go fast, but it doesn't have to be a few seconds. And it'll be, hold on a second, how much will each be worth on overall mark? So overall 10%, and I was thinking of setting it up so traditionally what I would normally do is make it so if you answer a question, you get 1 mark, and then if you answer correctly, you get another mark. But I'm thinking of doing, if you answer the question in general, you get 1 mark, and if you get it correct, you get 2 marks. It seems to kind of motivate people to try to do a little better. Is it strictly per participation, or will we get the mark as long as we answer? Right, so I think I answered that one. If you guys, again, most of you guys have reliable bandwidth. I don't think you guys are having problems. I mean, again, the questions aren't going to take a few seconds. I'll probably leave them up for at least a minute. So you should be able to see that. Okay, and as you guys can see, I don't know if you can see the poll right now, or what the answer is from the poll. So it's 64 in favor, 11 not, and 10 no answer. So again, the participation would say, okay, well, where is those other 10 people right now? Whether or not they're getting a coffee or they're just kind of logged in and left, like who knows, right? So it's going to motivate people to come to lectures to kind of be on top of the material. So overall, it's a better thing. And again, right now, it's not costing you anything. So it looks like you guys are in favor. So I'll post a message on the announcements. We might be able to start them today. And again, you guys don't need anything other than to download an app on your phone and register on their website. So I'll just kind of indicate the website. You say you're from the University of Windsor, it doesn't cost you anything. I think it does go through. It's just not sure. So you guys are answering, but it's not going through. Well, I'm seeing, I mean, I don't know what happens when you click on it. If it kind of highlights or whatever. Again, I don't know enough about Blackboard to tell you. So now, unfortunately, Blackboard can't use this poll. So this poll I just presented you guys doesn't show me who answers what. It's all anonymous. So I can't use it as a grading system. I mean, I can use it as a method for you guys to check things, but then I can't use it for participation grades. So in any case, I'll post something in the announcements, what website to go to, basically the procedure. It's very simple. And then you just add the class. You basically just say microprocessors, and then you'll find me there, and then we'll run it, and we'll do a test run maybe today. Again, we're going to have see you guys at 1 o'clock back here. Okay. Enjoy your next class. See you then.